Good morning everyone. Myself Sakshi Mittal, Assistant Professor in Department of Electronics and Communication Engineering, AKGEC Engineering College. Today in this my second lecture, I am going to discuss about the orbital elements for subject Satellite Communication KEC 062. So first we will start with the terminologies. What are the various terminologies related to the satellite, or I can say if I have to place a satellite in the orbit or I have to locate a satellite in the orbit, then what all terminologies are there which I should know. So first is the orbital radius. Orbital radius means the orbit is the path in which satellite is rotating. So we can say that if we talk about the orbital radius, it is the distance of satellite from the center of Earth. This is the path in which satellite is revolving, and here I have got the my planet Earth. Then this distance we call it as the orbital radius. That is the distance of satellite, or we can say it is the orbit radius. And altitude of satellite. So the height of satellite from the center of Earth, that is, we can say the orbit radius is something which is the distance from the center of the Earth and it is above the surface of Earth. So orbit radius will be calculated from the center of the Earth and the height of satellite will be calculated from the surface of the Earth. Then is the polar orbit. Now when satellite rotates in an orbit, like it is rotating in an orbit, my orbit, what all positions it will going to cover. So if the satellite rotates in an orbit over the north and south pole, if it is rotating like this, it covers the north and south poles, we say it is a polar orbit. Next is the equatorial orbit. Now when the satellite rotates in an orbit above the equator, I can say it is revolving in an orbit which is parallel to the equator. So we call it as a equatorial orbit. Or thirdly, we can have an inclined orbit. So if the satellite is revolving in the equatorial orbit and suddenly it gets tilted at some particular angle, we say it is in the inclined orbit. In my previous lecture, we have already discussed about the orbits. We have discussed about the polar orbit, equatorial orbit and the inclined orbit. Next is the ascending node. So the point where the orbit of satellite crosses the equatorial plane while going from south to north pole. See, now the satellite is orbiting. If satellite is orbiting, it depends on the direction. In which direction is it orbiting? Is it similar to the direction of the satellite of the Earth, or is it in the opposite direction? So we say ascending node is the point where the orbit of satellite, it crosses this equatorial plane while going from south to north pole. That is when it is going upwards at the point of intersection. Where is the point of intersection? We call it as a ascending node. Next is the descending node. So the point of the orbit where the satellite crosses the equatorial pole while going from north to south pole. So if it is coming, satellite is this, the satellite, if it is coming like this and it crosses the equator at somewhere here from north, south, so it will cut at 2 points, either while coming from north to south or while going from south to north. It can cut the equator at 2 points. So I am saying when it is coming from north towards the south, that is in the downward direction, we call this point of intersection as the descending node. And when it is going upwards, that is from south to north pole, then this point of intersection with the equatorial plane, we call it as the ascending node. Next is the term the line of node. So the line joining this ascending point and descending point. This is my ascending point, this is my descending point. So the line joining this point and which passes through the center of Earth, we call it as the line of nodes. Next is the term is the equinox. So what is the equinox? Equinox is the day on which period of day and night are equal. It actually happens twice a year when the my day length is equals to the night length. It happens twice a year. First one, it lies on the 21st March. We call it as a vernal equinox. So vernal means spring weather. So 21st March, the period of night and the period of day, they are equal. Second one is the autumn equinox. It lies on 23rd September. Autumn is actually third season of the year. So equinox is, we can say the both day and night period are equal. We call it as a equinox. Next is the first point of Aries direction. So, a direction of a line joining center of Earth to the center of Sun at vernal equinox. That is on this particular day, the direction of line which is joining the center of Earth with the center of Sun, we called it as the first point of Aries direction. Next, we are going to discuss about the orbital elements. Now, these are the major orbital elements related to locate a satellite in an orbit. First one is the eccentricity, then semi-major axis, right ascension of ascending node, inclination, argument of perigee, time of perigee passage. See, in eccentricity, it generally describes how much circular your orbit is, or it gives a measure of how much circular your orbit is, or you can say how is it a perfect ellipse. Then the semi-major axis. Major axis is the longest distance in your orbit. So, we can say if we divide that by 2, it gives us the semi-major axis. So, eccentricity and semi-major axis, they both are related to the shape of your orbit. The eccentricity is denoted by small e here and semi-major axis by a. Then right ascension of ascending node. In the previous slide, we have already discussed about the ascending node. So, ascending node is a point when satellite orbit, it cuts the equatorial plane while going from south to north pole. So, we will see what is this right ascension of ascending node, which is represented here by this symbol ohm. Then is the inclination. So, inclination means we have discussed about the two orbits. One was the equatorial orbit, when my satellite is in an orbit above the equator, or I can say it is revolving parallel to the equator. Second, we have discussed when it is covering north and south poles. So, it is revolving like it is covering north and south pole. Now, I am saying instead of over the equator, if this is the equatorial plane or this is covering the north and south poles. Now, I am saying the orbit should be such that it is this gets tilted with respect to the equator like this. So, this angle we call it as the inclination. How much your orbit is tilted with respect to the equator, denoted by I. Next is the argument of perigee. So, first we will discuss what is a perigee. So, then the angle which it is making, it will be represented by omega. Next is the time of perigee passage. The satellite, when it moves across this point, perigee point, then that particular time we denote it as a TP. Now, see in this particular slide, first we are going to discuss about the perigee and apogee, and we can also call them as the periapsis and apoapsis. Now, see in this particular diagram, what is actually happening? The satellite is revolving in an orbit around the Earth, which is highlighted by this color here, by this white color. Now, see, there are 2 points, perigee and the apogee. Perigee is the point which is closest to the sun, closest to the Earth, and apogee is the point which is farthest from the Earth. So, perigee is the closest point to the Earth and apogee is the point which is farthest from the Earth. Now, observe one more thing. Perigee is the closest point. The satellite, when it is going from this perigee point, the speed of the satellite is comparatively high while it is crossing the apogee point. See, just check this here. While it crosses this periapsis point, the speed of the satellite, it is comparatively high, and now it is crossing this apoapsis point, which is the farthest from the sun or the Earth. Then the satellite speed is comparatively slow. The reason being, we can say that when it is at the perigee or it is in the dark area of the Earth, then it crosses it very fast, so that it gets maximum time to be in front of the Earth. For it is actually, it can be used for the communication purpose, because the satellite is in front of the Earth, so it can be used for communication. So, perigee is the point closest to the Earth, apogee is the point farthest from the Earth, and we can say the satellite is the speed of satellite, it is relatively higher while it crosses the perigee point, and it is relatively slower while it crosses the apogee point. Next is the semi-major axis. Now, see, if this is the Earth, I have a certain distance towards the perigee, I have certain distance towards the apogee. So, the if the semi-major axis denoted by a small letter a, the major axis we calculate, the major axis is the total distance, that is if it is the perfect shape, it is a perfect ellipse. The longest distance, that is the perigee to the apogee, the longest distance we call it as a major axis. If I have to calculate the semi-major axis, this longest distance, it will be divided by 2, it will gives us the semi-major axis. So as it can be revealed from this, so semi-major axis is the half of major axis, and major axis is nothing but the distance between my perigee and apogee point. Again, we can visualize that the speed of satellite is varying in perigee and apogee points. Next term is my eccentricity. So now we have to calculate the eccentricity. So this is a perfect ellipse shape which is for the orbit of a satellite. Now we say that we know we need to calculate the eccentricity. Eccentricity denotes the shape of the ellipse, how perfectly ellipse it is or how perfect a circle it is. So you can calculate this eccentricity using the formula C by A. See, in this particular figure, this is the C. We have denoted them A, B and C. So with the Pythagoras theorem, we can replace it with under root A square minus B square by A. So we can calculate the eccentricity using this formula. Now the relation between eccentricity and semi-major axis. Now see, what all shapes of orbit we can have. We can have it to be a circle, ellipse, or can we have it to be a parabola or a hyperbola? Now in case of if my eccentricity is 0, that means the shape of orbit is perfect circle, and if eccentricity lies between 0 and 1, then it is an ellipse. But what about the hyperbola or parabola? See, like in the previous slide, we have seen that it has got two focal points, f1 and f2. So you need to have both the points on this axis so that you can calculate your major axis, your minor axis. But in case of hyperbola, the eccentricity, it will be greater than 1, as you cannot locate where your other focal point is. So the shape of orbit, it can be circle or it can be an ellipse. Now see how with the eccentricity varies with the shape of orbit. As in the first one, the green circle, the eccentricity is 0, it is a perfect circle. And as the eccentricity is approaching towards 1, like towards 0.95, this the red one, it shows that the shape of orbit is ellipse. Now this is the diagram for the geocentric equatorial subordinate coordinate system. So first is the reference section. So this is the reference plane. Then we have taken it as a argument of periapsis, that is argument of perigee, you can say. Then this omega. This is the orbit of satellite. It is inclined at some angle, which is my inclination. This, the gray one, this is my equatorial plane, and this is this orbit of satellite. So this satellite, while revolving, it is inclined at some particular angle, which we denote as by I, that is the inclination. Now see here, this is this point when my orbit of satellite, it cuts the equatorial plane while going from south to north pole. So we call it as the ascending node. Here you have it as a descending node. Next one is the angle. So the right ascension of ascending node. So the angle which it makes, your equator makes with the ascending node, this gives your ascending node, it is denoted by your ohm. That is your longitude of ascending node. So now we'll see in this diagram about the inclination, how we calculate the angle of inclination. The first thing is the satellite which is orbiting. Is it orbiting in the direction similar to the Earth, or is it in the opposite direction? Like in this particular figure, we can say that the satellite which is shown by, which is orbiting in the orbit, which is moving in an orbit, which is shown by this white color, when it is in the same direction, when it is rotating in the same direction, we call it as a prograde. See again, if it is covering, now see, this is the satellite, it moves in an orbit and it is in the same direction. This is the color, red color is indicating the orbit of satellite. This is my equatorial plane. So we call it as a prograde orbit. So because it is moving in the same direction, we call it as a prograde orbit. In this, now it has tilted, the direction is reversed now. So if it is moving opposite direction, we call it as a retrograde, that is a indirect. And when it is covering the north and the south poles, we call it as a polar orbit. Next is the right ascension of ascending node. No, so again check, the satellite is moving in an orbit, in a perfect ellipse orbit. So this is my north pole, this is my south pole. So now it is moving, as you can see, it is farthest from the earth. So the speed was slow comparatively. Now it cuts the equator at particular point while going from north to south pole. We call it as a descending node. Now it is going from south to north. So it cut at this point. We call it as a ascending node. We have already discussed in the previous one. Now the vernal, that is the equinox direction, we said that it will be the point joining the center of the sun with the center of earth at the vernal equinox, that is on 21st March. So this is my first direction of Aries. Now the angle which this ascending node makes with the first point of Aries direction, we call it as a right ascension of ascending node. Again check in the figure. So this, the angle which it makes here, it is my right ascension of ascending node. So we can again say that the angle which the right ascension of ascending node, the angle between vernal equinox direction or your first point of Aries direction and the ascending node is called as the right ascension of ascending node. Next is the argument of perigee, which is denoted by omega. So we'll again check, this is my equatorial plane. Now the satellite is moving in an orbit which is shown by this blue color. Again it cuts the equator at one point, that is the descending node. While going from south to north, it again cuts at another point, ascending node. So this argument perigee, now see, it is the angle, it will be shown in the red color. So it is the angle between ascending node to the perigee. So the blue color, this white color, it is the movement of satellite. So it is moving from north to south. It cuts at a point called descending node. While going upward, it cuts at ascending node. Now this red color shows the angle which ascending nodes with the perigee point. Perigee is the closest point to the earth. So argument of perigee, it is nothing but the angle between the ascending node and the perigee point. So if we have to locate the satellite with respect to earth, what all terms we need to know? First is the epoch. So epoch is the specific time at which position of satellite is specified. So any relative time at which you want to specify the location of a satellite, or which you want to locate, specify the position of a satellite, we call it as an epoch. Next is the eccentricity, denoted by E. So half of the distance between foci of an ellipse, if I have two focal points, so half of the distance between that ellipse, between the foci of that ellipse, we call it as a semi-major axis, because the longest distance we call it as a major axis, the smallest distance is the minor axis, and the half distance between that we call it as a semi-major axis. So we can see it is the measure of how out of round an ellipse is. And eccentricity of 0, it would be a circle. Next is the perigee, or we can say the perihelion. It is the point in an orbit when satellite is closest to the earth. Like in the previous slides, I have shown a GIF in which we have seen the point which is closest to the earth, we call it as a perigee. If it is closest to the sun, we call it as a periapsis or perihelion. Same way apogee, it is a point in the orbit when satellite is farthest from the earth. Same way aphelion. Next is the line of apsides. Now, what is this line of apside? Like we have seen the line of node, the point joining the ascending and descending node from the center of earth, we call it as a line of node. Same way, line of apsides, the line joining my perigee and apogee through the center of earth, we call it as a line of apsides. Next is the period. Now, what do we mean by the period? So, the time it takes the satellite to complete one orbit is called as a period, or you can call it as a time period, which is generally denoted by T. So, we can say when satellite is moving in an orbit, it can be a polar orbit, it can be equatorial orbit, it can be inclined orbit. So, whatever time it takes for the satellite to complete one orbit, that means from where it has started, if it has to one rotation, it has to reach at that particular point from where it has started. So, we call that time as the time period. Then is the semi-major axis. So, it is the half of the longure of two axes of the orbital ellipse. So, I have ellipse. So, if I say this is my major axis, the longest distance, so half of this will be called as your semi-major axis. Now, the semi-minor axis. So, before the semi-minor axis, you need to know the minor axis. So, the shortest distance in the ellipse, we call it as the minor axis. Now, half of this will be called as the semi-minor axis, that is denoted by B. Now, is mean anomaly. What is this mean anomaly? So, the angle that a satellite would have moved since last passing perigee or perihelion point, assuming that the satellite moved at a constant speed in an orbit on circle of the same area. See, if the orbit is circle, the speed of satellite will be constant. But if the orbit is ellipse, the speed will be varying. It will be high at a perigee point, it will be relatively slow at apogee. So, we are saying the angle that a satellite would have moved since past perigee point, it was on perigee, now it has moved to certain distance. So, the angle that is making, assuming that satellite is moving at a constant speed in a circle of same area as the actual orbital ellipse. So, that circle which we are assuming, it has the same area as the ellipse. So, we can say the if I say this is my perigee point and the satellite it has moved to this particular point, I want to calculate the distance, this distance. So, we can say the time, the angle which the satellite have moved, how much distance it has covered from this perigee point, we call this particular angle as the mean anomaly. So, it is nothing but we can say it is actually a distance in arc. So, angle that satellite would have moved since last passing perigee, assuming that it is in a orbit which is circular in shape and it has the same area as my actual orbital ellipse. So, now what is true anomaly? So, the actual angle that a satellite has moved since the perigee is actually your true anomaly. In case of mean anomaly, we have assumed it to be a circular orbit, although it was an ellipse orbit. So, now the true anomaly says that the actual angle that the satellite has moved since the last perigee point, we call it as a true anomaly. Now, in the particular diagram, we have mentioned the xi-axis. It is from the center of Earth towards a fixed location in a space called the first point of Eris, or you can call it as a vernal equinox, which lies on your 21st March. So, first point of Eris, it is denoted by here with the xi-axis. So, xi-ya plane, it contains the Earth's equator and is called as the equatorial plane. So, whatever you have to mention any angle, you will be mentioning it with respect to xi-ya plane. So, xi is your first point of Eris direction, that is your vernal equinox. So, the angular distance measured eastward in the equatorial plane from xi-axis is called the right ascension of ascending node, and you give it by symbol Ra. Like in the previous diagrams also, we have seen that if like this is my coordinate system, I have my xi here, that is my first point of xi is here, and let's say I have this somewhere, this is my ascending node. So, the angle, this angle we call it as the right ascension of ascending node. So, the angle between the first point of Eris and the ascending node, which will be measured in the eastward direction, we call it as the right ascension of ascending node, given by symbol Ra. So, the point at which orbit penetrates the equatorial plane, we called it as node, and the satellite moves upward to the equatorial plane, we called it ascending node, and if we move it downwards, that is towards the south pole, we call it as a descending node. So another term for the right ascension of ascending node is the longitude of ascending node. It is the angle of ascending node, again measured eastward of the vernal equinox along the equatorial plane. Next is the argument of perigee. It was denoted by omega. So the angle between ascending node and the perigee point measured counterclockwise along the plane of orbit. So the angle which my ascending node will make with the perigee point, and we will be moving counterclockwise. Time of perigee passes. So time at which a satellite last passed the perigee is the time of perigee passage. Or you can say, if you want to measure it at a particular time, so you can say the time difference between how much time it has taken or how far it has come from the perigee point. So the inclination, the angle between the plane of orbit and the plane of celestial equator for Earth orbiting satellites. So we can say the plane of the orbit, if it has got tilted somewhere with respect to your equatorial plane, we call it as a inclined orbit, or it is tilted at some particular angle, which is your inclination angle. Now we can say, if we have to locate the satellite with respect to the Earth, so this is the satellite, it is moving in this particular orbit. Now, so what, how can we relate? First thing I got to know is this xi. Xi is the first point of Aries direction. Now, while moving, the satellite is moving in this particular orbit, it will come and it will cross this equator at this particular point while going from south to north, ascending node. The angle this orbit is making with the equatorial plane is called as your inclination. The angle between your ascending node, this particular, with the perigee, this is your argument of perigee. Angle between first point of Aries direction and the ascending node, it is your right ascension of ascending node, denoted by ohms. So if we know all these things, if I know the inclination, then I know where my orbit is. If I know this point, this omega, how far it is, then I can locate the perigee point. So if we know these 6 orbital elements, it is possible to locate the satellite from where the satellite is actually in the orbit. Next is about the eccentricity and semi-major axis. So from this figure, it is clear that if I have the orbit in the circular shape or it is in the ellipse shape, then it is possible. Like for the parabola and hyperbola, the other focal points, they are unknown. We don't know where it is. So they can be anywhere in the infinity. So we say that the orbit will be, it will not be complete. So the shape of orbit, it can be circle or it can be the perfect elliptical orbit. So this diagram also, it shows like in case of hyperbola and parabola also, the second focal points, they are missing. So if another focal points are missing, we cannot have a perfect orbit. So the shape of orbit, it can be circle or it can be an ellipse. Now based on these parameters, we'll discuss 2 examples. First one is a satellite is an elliptical orbit with a perigee. So perigee was the point which was closest to the Earth. It is at a distance of 1000 km. Apogee is at a distance of 4000 km. So it was the point which was farthest from the Earth. Now the mean Earth radius. So it is a constant which we all know. It is 6378.14 km. We have to calculate the period of orbit in hours, minutes and seconds and the eccentricity. So let's see. If this is the satellite orbit, here I have the Earth. This is perigee point. This is my apogee point. So it says the elliptical with the period of perigee is at a distance 1000 km. So this distance I have height of perigee. This distance I have height of apogee, which is actually 4000. It is 1000. It is 4000. We have to calculate the eccentricity. So for eccentricity, I must be having this A, semi-major axis. So this is the Earth. So we knows the diameter of Earth, that is 2 into radius of Earth. So radius of Earth is 6378.14. So into 2, we know the complete diameter. And if I add height of perigee and height of apogee, I can say I've got the major axis, which is denoted by 2a. So from here, we can say 2a is twice Re plus height of perigee plus height of apogee. So we can calculate in this manner the value of semi-major axis. So if I have got a, if a is known, I have to calculate the time period, that is the orbit period. So how can I calculate? Using Kepler's third law. So Kepler's third law says t square is equals to 4 pi square a cube by mu. So this a, the semi-major axis, we have calculated it, and mu is again a constant. So in this way we can calculate the time period, which comes out to be 8325.1864 seconds, or if you convert it into minutes and seconds, it is 138 minutes 45.19 seconds, and if you convert it in hours, then it is 2 hours 18 minutes 45.19 seconds. So the first part of the question, that is the time period, it has been calculated. Now second, I have to calculate the eccentricity. So we can say we can have a relation like if I have got a radius of the Earth plus the height of perigee, I can say it is a1 minus e, or you can say the radius of Earth plus height of apogee. Radius of Earth plus height of apogee equals to a1 plus e. So you can use either this relation or this relation, and we can calculate the eccentricity, which comes out in this particular case to be 0.169. So we have used radius of Earth plus height of perigee, both are known, equals to a1 minus e. A we have already calculated, so eccentricity comes out to be a 0.169. That means it is a shape is elliptical. Next one, so we have got a SpaceX mission to the ISS, is an example of a low Earth orbit satellite, and it says that it has to insert it into a circular orbit 250 km above the Earth's surface, and the radius of Earth is this particular kilometer. We have to calculate the time period. Again, we have to calculate the time period. So first thing is the radius of Earth. We know the height from the surface of Earth. So you need to calculate a. So a will be Re plus h. So this is the radius of Earth. This is the height above the surface of Earth. So we calculate this a. Now time period, again we can calculate using Kepler's third law. T square equals to 4 pi square a cube by mu. So we have calculated the time period using this formula, which comes out to be 89 minutes 30.3 seconds. And it is always better to convert the time in hours, minutes and seconds. Next, we have to calculate the velocity. So velocity we can simply calculate using this formula from the Kepler's third law again. V equals to under root mu by r. So the velocity, it comes, we have a mu which is constant 3.98 second 10 to the power 5. R is again Re plus h. It will yield the velocity to be 7.755 km per second. So in this particular lecture, we have discussed about all the orbital elements which are needed to locate a satellite in the orbit, or if I need to know the location of a satellite, if I want to locate it, what all parameters I need to know. So we have discussed about those parameters, and the references, these are the two textbooks which I have used for this particular lecture: B. Pratt, Satellite Communication, and D. Rodney. So this was all about it.